So in the last video, we talked about the fact that the Earth's system of the Earth's surface and the Earth's atmosphere would be a black body if it did not have greenhouse gases. And that would mean, as a black body, that this Earth system would absorb completely and emit completely, 100% both ways. Absorb everything it could and emit everything it absorbed if the Earth's atmosphere did not have greenhouse gases. But we couldn't live there because it would be much too cold to have liquid water. And the fact is that the Earth's system does have greenhouse gases. And the Earth's atmosphere does absorb not everything. The Earth's atmosphere absorbs selectively. A perfect absorber would absorb everything. The atmosphere doesn't do that. The atmosphere absorbs through greenhouse gases very specific wavelengths. And as such, the Earth's atmosphere is not a black body as part of the Earth's system. Now, if that's the case, we can still acknowledge that while the Earth's atmosphere is not a black body, and the Earth's atmosphere has selective absorbers, but the Earth itself, the surface of the Earth, can still remain a black body. It will absorb less because the atmosphere is doing some selective work of absorption, but the Earth's surface can still emit everything that it absorbs. So we have this hybrid model here. Let's explain that a little bit more. Without greenhouse gases, the Earth would need to absorb everything and emit everything. With greenhouse gases, the atmosphere will absorb selectively and allow more warmth so that we don't have an icy environment. And in absorbing in the atmosphere, those greenhouse gases will emit energy as well. And they will emit it going back out to the atmosphere and back out to space. And that energy will also ping pong and be emitted down to Earth. So the greenhouse gases get involved. The greenhouse gases will still emit. They'll just emit in different directions that really hamper the ability to emit directly and emit in the same direction that you absorbed. You absorb through space, you should emit through space. But with the greenhouse gases, they tend to emit through space and they emit back down to Earth, which is an issue. This is a case where we make an observation about radiative equilibrium, and then we want to apply math to it. And in fact, the math has only been applied to this radiative equilibrium issue with our atmosphere and greenhouse gases since we've had very advanced satellites go up. So this is a very new type of science, and now we want to start putting data to this science. Let's look at what we have, and this is an area that you can certainly get involved in because it is so new and we need so many new ideas. So this is putting some numbers to our observations. Here are our observations over here. We have units of radiant energy coming in from the sun. Let's say we had 100 radiant energy units. We'll just start with 100 because it's easiest. The NASA models actually take this down to number of joules. We won't go that far right here. Let's say we have 100 units of radiant energy. That radiant energy is a combination of high energy UV energy, ultraviolet energy, and a little bit lower visible energy, which we see, and then quite a bit lower infrared energy. That's all coming at us as photons, as 100 units of solar energy. That's what we'll call it. But it's actually many thousands of wavelengths in 3 different sectors: ultraviolet, visible, and infrared. So if we have those 100 units coming in, what happens to those 100 units? Let's look into it. We can apply the math over here. We'll start with number 1. We have 100 units of solar radiation coming in: ultraviolet, visible, infrared. Let's go to number 2 and see what happens. Well, right off the top, you're going to get some of that radiant energy transferred by reflection. And that reflection can either be that specular reflection right off at the same angle, or it can be that scattered reflection that we looked at in terms of the colors of the atmosphere. So right off the top, you're going to get some scattering in the atmosphere, about 6 of the 100 units. And then you're going to get reflection from the clouds, generally specular reflection from the clouds, and that's about 20 units. You see this in cumulus clouds that are just bright white. They're reflecting, the incoming solar energy is reflecting off those clouds. In addition, you're going to get some reflection right off the Earth's surface. The Earth has some reflectivity, as we know from water and from the chart that we saw with the Earth's surface on it. You're going to get about 4 units of that. Altogether, about 30 units of the incoming 100 are reflected off directly, and they are not absorbed by the atmosphere, and they are not absorbed by the surface of the Earth. Well, let's look at number 3 here. What is absorbed by the atmosphere? What is absorbed by the greenhouse gases? About 19 of the 100 units are absorbed by the atmosphere and the greenhouse gases that are associated with it, and the clouds, which have the biggest greenhouse gas, which is water vapor. So about 19 units of the incoming solar radiation are absorbed by the atmosphere and the clouds. The atmosphere tends to absorb the ultraviolet rays. The clouds tend to absorb the infrared rays that come in. And as we know, when the atmosphere and the clouds absorb this energy, it does go back to space, some of it. But that's where you get these ping pong effects, this ping pong table effects. And you have some energy that actually ping pongs back down to the surface. So let's look into that a little bit more. When that energy from the infrared emissions comes down to the ground, it gets ping-ponged back up again so that the ground will absorb the IR and then emit it off. And you'll see that in here as well. The ground is emitting off this IR. As a result of this ping-ponging, we're not noting perfect absorption. We're not noting that the atmosphere is a perfect black body because it doesn't emit off right in the direction that of the source. But as a result of that, we've got an Earth that we could live in. It's at about 57 degrees Fahrenheit, average pole to pole and equator in the middle, 365 days a year. We average about 57 degrees Fahrenheit. And when we talk about the Earth gaining warmth, we talk about that number and the average over the year, pole to pole with the equator in between. That's as a result of this ping-ponging effect of the greenhouse gases. Glad we have a warmer Earth as a result of greenhouse gases. But in doing so, did we maintain the fact that the Earth's surface is a black body? The Earth's surface is in radiative equilibrium. Does the Earth's surface emit as much energy as it absorbs? Well, how much energy does the Earth's surface absorb of those 100 units? The Earth's surface absorbs 51 of those units. And does it emit that? Actually, it does. So that Earth's surface, highlighted here in green, actually will emit out 51 units. It will emit out 7 of those units in convective and conductive processes, 23 of those units in latent energy processes of evaporation, and it will also emit out a portion of it in infrared. You see one of these arrows emitted in infrared. We'll explain the rest of the hours in a few minutes. Well, what about this extra IR over here? This extra IR is due to the fact that the Earth's surface absorbed higher power visible radiant energy. The visible radiant energy has more energy in it than infrared. Infrared is a lower energy wavelength. So in emitting out the same total energy, that means the Earth has to emit out, since it's not emitting out the same energy, visible energy, it is emitting out lower energy IR. It's going to emit out more lower energy IR to balance the amount of energy and come up with an equilibrium of the amount of energy that it took in. So as a result of that, the Earth's surface emits out more IR. And when that happens, that IR can be trapped in the Earth's atmosphere and get ping-ponged back down again. So that while the Earth's surface is emitting out everything that it absorbed, we are getting the impact of the IR getting trapped by the atmosphere and ping-ponging back down again. Take a look at that energy level difference between the total energy that the sun emits and the total energy that the Earth emits. Here is a representation of the black body curves of the sun and the Earth. And in terms of that, the black body curve says that the sun is emitting out quite a bit of ultraviolet light in this wavelength, an enormous amount of visible light in these wavelengths in nanometers, and then quite a bit in the infrared spectrum. Here's the infrared spectrum down here. And about 37% of the sun's emission is in the infrared spectrum. So that's a total of an enormous amount of energy. Here's the Earth's black body curve, and this is actually not even to scale. The Earth's black body curve should be smaller than this, but I couldn't get it to the point where you could actually read this. The Earth's black body curve shows emissions farther down the spectrum in the infrared areas. This is near IR at 1.0 nanometers, 1.5 nanometers. The Earth doesn't start to emit until 5 nanometers, and it peaks at 10 nanometers. And of course, the total emission is much lower. So if we are supposed to equilibrate the amount of energy from the sun emitted and the amount of energy from the Earth emitted, this isn't showing that. But that's not really the case, because the Earth does not absorb everything that the sun emits. In fact, those greenhouse gases are here, and they are absorbing in purple just about all of the infrared, all of the ultraviolet coming in from the sun in purple. You have about 100% absorption here. You have very little absorption of the Earth's atmosphere when it comes to the visible light coming from the sun. That's why we see such beautiful colors. And we have uneven absorption in the infrared spectrum. So we are not absorbing everything that the Earth puts out at the Earth's surface. We're absorbing just a bit of it. That's why we only have to emit a bit of it. And in fact, when we do emit, we have to make sure we have a clear vent